Let me go back now to the question I asked at the beginning. I said that one of these transformations is called matrix transformation. Well, that's obvious. Or linear transformation. What does that mean? How is this thing linear? Well, first of all, a matrix transformation is linear in the sense that it preserves linear combinations. Now, what does that mean? That means if I take a linear transformation, notice that now I'm using the letter T instead of the letter L. That's another letter that is used to denote a transformation. Of course, it's a linear transformation, so I can use either L for linear or T for transformation. Since I'm going in this particular situation, I'm going to show you that this thing is linear. I'm starting by not assuming that it is, so I'm going to call it a transformation. So let's pick a matrix A and let's see what it does to a linear combination of the type AU plus BV. Is what is coming out of this transformation, does it still respect that linear combination structure? Well, let's see. How does the transformation work? Transformation works by multiplying A times the linear combination. But once again, distributivity does exist for matrix product, so this is equal to this new expression. Now, in each of these two terms, we have a product of matrices and a scalar. Well, we know that the scalar can be moved anywhere we want. Although there is no commutativity for product of matrices, there is commutativity when it comes to scalars. So I'm going to move both of the scalars in front, and I'm also going to use the associativity to write it in this new way. But what is AU? Well, AU is the image under the transformation of U. And AV is the image under the transformation of V. Therefore, I can rewrite this last expression as A times dA of U plus B times dA of V. So notice that now the same linear combination that we had at the beginning, AU plus BV, exists at the end, except on the images. And that is the sense in which we say that the matrix transformation preserves linear combinations. Therefore, it is linear. So what I've just shown you is that any matrix transformation is linear. Being a linear transformation, so the fact that it preserves a linear combination, means that any matrix transformation will change straight objects such as lines and planes into other straight objects. Okay? Although the new straight objects may not be of the same type. Okay? So if I start from a line and I apply a linear transformation, or a matrix transformation, sorry, to this line, I know that I'm going to end up with either another line or maybe just a point, but something has to be linear. I cannot come up with a parabola or any curved object. Similarly, if I take a plane, say in a higher dimension, so let's say I pick a plane and I figure out what happens to the plane under the transformation. Since the transformation is linear, I know for sure that the image of that plane is going to be either another plane or maybe a straight line or maybe a single point, but it's got to be something straight. It cannot be anything curved. You might wonder, well, could it be a hyperplane or something like that? We're going to look at that in one of the later classes. Let me show you now why I said earlier that not only every matrix transformation is linear, but it turns out that every linear transformation is a matrix transformation. So every transformation involving vectors, which preserves linear combinations and therefore it's linear, turns out to be a matrix transformation. So there is a matrix that generates it. Well, let's see how that works. So what I want to show is that every linear transformation is a matrix transformation. So let's look at the proof. Let's assume that we have a transformation from Rn to Rm. Remember, transformation is just the linear algebra jargon word for function. Okay? So let's say we have a function, and let's suppose that this function is linear. So in other words, that it changes linear combinations to linear combinations on the other side, the same linear combination on the other side. And now consider the vectors vi, which are the images under this transformation of the standard basis for Rn. So vi is going to be the image of ei for I equal to 1 to n. Okay, so v1 is t of e1, v2 is equal to t of e2, etc. All right, now let's pick a vector in Rn. Okay, and this vector in Rn will have components x1, x2, xn, which means that I can write that vector as x1 times e1 plus x2 times e2, etc., plus xn times en. Right? It's a standard basis. In a standard basis, the components are the same as the coordinates. All right, so now let's see what happens to this vector. under the transformation? Well, T of x is going to be equal to T of that linear combination because x is that linear combination. But I just said that, or we're assuming that T is a linear transformation, which means it preserves linear combinations. So that means that the image of x under T can be written as that linear combination. But remember, T of E1 is what we decided to call V1, T of E2 is V2, and so on. And these are generic vectors. We don't know what vectors they are, but we just know that they are vector in our M. Okay, so what that means is that I can write my image of x under T in this way. Now let's see where that leads us. That leads us to the following thing. It leads us to the fact that I can write T of x as a product, as if you want a dot product or a matrix product of V1, V2, Vn times x1, x2, xn. But remember, V1, V2, Vn were vectors, and therefore what I have on the left hand side is a matrix, okay? And that's exactly the matrix that I claimed was going to be there. Okay? So therefore, what we have shown is that every linear transformation is in fact a matrix transformation, is defined by a matrix, and the matrix is obtained by considering the images under the transformation of the standard basis for the domain.